Hello, today we're going to dive into the world of rational functions, focusing on how to find their zeros and how to solve inequalities involving them. This is AP Precalculus, topic 1.8, rational functions and zeros. By the end of this video, you will be able to find the real zeros of a rational function and use those zeros, along with vertical asymptotes, to solve rational inequalities. These skills are fundamental for understanding the behavior of complex functions. First, let's establish what a rational function is. A rational function is a function r of x that can be written as a fraction, p of x over q of x. Here, p of x and q of x are both polynomials. The most crucial part is that the denominator q of x cannot be 0. If the denominator is 0, the function is undefined at that point. Our main goal here is to find the zeros of these functions. Zeros are simply the x values that make the entire function equal to 0. Look at our function r of x equals p of x over q of x. To make this fraction equal to 0, the numerator p of x must be 0. Think about it. The only way to get a 0 result from a division is if the number on top is 0. So we say that real zeros occur when the numerator p of x is equal to 0. But there's an important condition. The value you find must be in the function's domain. In other words, you can't have a 0 where the denominator q of x is 0. Remember, zeros cannot occur where the function is undefined. To put it clearly, real zeros are the x-intercepts of the graph. These are the points where the function crosses the x-axis, which only happens when the numerator is 0. So, to recap, zeros are the x values that make the function output 0. For a rational function, this only happens when the numerator is 0 and the denominator is not. Now, let's look at a key concept that's the counterpart to zeros, the vertical asymptote. We know that zeros happen when the numerator is 0. So, what happens when the denominator is 0? When the denominator q of x equals 0, the function is undefined. This creates a vertical asymptote, which is a vertical line that the graph of the function approaches but never touches or crosses. Think of it as a barrier on the graph. As the x values get closer and closer to a value that makes the denominator 0, the y values of the function shoot off to positive or negative infinity. For example, consider the function f of x equals 1 over x. The denominator is 0 when x equals 0. The graph has a vertical asymptote at the y-axis, the line x equals 0. Notice how the curve gets infinitely close to that line but never actually touches it. It's critical to understand that a vertical asymptote is a place where the function is undefined, while a 0 is a specific point on the graph where the y value is 0. However, sometimes there's a special case. If the numerator and the denominator share a common factor, they will both be 0 at the same x value. When this happens, the graph of the function doesn't have a vertical asymptote. Instead, it has a hole, a single missing point. The graph behaves exactly like the simplified function, but with that one point removed. Let's summarize. Denominator zeros are important. If there's no common factor, you get a vertical asymptote. If there is a common factor, you get a hole. Let's put this into practice with a formal method for finding zeros. We'll use a step-by-step process. Here is our 4-step plan to find the zeros of any rational function. Let's work through an example together. Consider the function r of x equals x squared minus 9, all divided by x squared plus x minus 6. Step 1 is to factor the numerator. The numerator, x squared minus 9, is a difference of squares. Step 2 is to factor the denominator. The denominator, x squared plus x minus 6, is a quadratic trinomial. Now, let's rewrite the function using its factored form. So r of x is x minus 3 times x plus 3 divided by x plus 3 times x minus 2. Step 3 is to identify common factors. Notice that both the numerator and the denominator share the factor x plus 3. Because of this common factor, the graph of this function will have a hole. The hole occurs at the x value that makes this factor 0, which is x equals 3. The common factor can be canceled out, as long as we remember that x cannot be 3. This simplifies the function. The simplified function, let's call it s of x, is x minus 3 over x minus 2. This is the function that our graph looks like, just with a hole at x equals 3. Step 4 is to find the zeros by setting the remaining numerator factors equal to 0. The remaining numerator factor in our simplified function is x minus 3. Setting x minus 3 equal to 0 gives us x equals 3. This is our 0. The x-intercept is at x equals 3. Let's double-check our work. We found a 0 at x equals 3. We also found a vertical asymptote at x equals 2 from the simplified denominator. And we found a hole at x equals 3 from the canceled factor. Now that we can find zeros, we can use them to solve rational inequalities. These are problems that ask us to find when a rational function is greater than, less than, or equal to 0. The zeros of the numerator and denominator play a crucial role here. The zeros of the numerator and the denominator are the critical values that divide the number line into intervals. Within each of these intervals, the sign of the entire rational function will be constant, either always positive or always negative. Let's review what each type of zero means for our number line. Numerator zeros are where the function is equal to 0, so these are possible endpoints for our solution. Denominator zeros, which give us vertical asymptotes, are points where the function is undefined, so they can never be included in our solution set. They are strict boundaries. So, our method for solving rational inequalities is to first find all critical values, the zeros of the numerator and denominator, and plot them on a number line. This creates intervals. Then we choose a test value from each interval and plug it into the simplified function to see if it's positive or negative. The intervals that satisfy the original inequality are our solutions. This process of using a number line to check intervals is sometimes called a sign analysis or a sign chart. Let's work through an example of a rational inequality. This will tie together everything we've learned. We want to solve the inequality. X minus 3 over x minus 2 is less than or equal to 0. Step 1. Find the critical values by setting the numerator and denominator to 0. The numerator is 0 when x equals 3. The denominator is 0 when x equals 2. Our critical values are 2 and 3. Step 2. Plot these critical values on a number line to create our intervals. We draw a number line and mark 2 and 3. This divides the line into 3 intervals, K2, 2, xy3, and xy3. Let's think about the endpoints. The value x equals 2 makes the denominator 0, so the function is undefined there. This means 2 can never be part of our solution, even though the original inequality includes equal to. We'll mark it with an open circle or parenthesis. The value x equals 3 makes the numerator 0, which makes the function equal to 0, so 3 is a solution. We'll mark it with a closed circle or bracket. Step 3. Test a value in each interval. For the interval x less than 2, let's test x equals 1. Plugging it in gives ich2 divided by 1, which is positive. 2. This is not less than or equal to 0, so this interval is not a solution. For the interval between 2 and 3, let's test x equals 2.5. Plugging it in gives negative 0.5 divided by positive 0.5, which is negative 1. This is less than or equal to 0, so this interval is a solution. For the interval x greater than 3, let's test x equals 4. Plugging it in gives positive 1 divided by positive 2, which is 0.5. This is not less than or equal to 0, so this interval is not a solution. Step 4. Write the solution. The only interval that satisfies the inequality is between 2 and 3. In interval notation, our solution is from 2 to 3, with a parenthesis at 2 and a bracket at 3. This means x is strictly greater than 2, but less than or equal to 3. Let's double check. At x equals 2, we have division by 0, so it's excluded. At x out 3, we have 0, 1, which is 0, and 0 is less than or equal to 0, so it's included. This confirms our solution is correct. Let's work through one more, slightly more complex example to solidify our understanding. This time, we want to solve x squared minus 4 over x is greater than or equal to 0. Step 1. Find critical values. Factor the numerator first. The numerator x squared minus 4 factors to x minus 2 times x plus 2. The denominator is just x. Setting the numerator to 0 gives x equals 2 and x equals 2. Setting the denominator to 0 gives x equals 0, so our 3 critical values are 2, 0, and 2. Step 2. Plot these values on a number line. We mark 2, 0, and 2 on our number line. This creates 4 intervals. The values 2 and 2 make the numerator 0, so the function is 0 there. They are included in our solution. The value 0 makes the denominator 0, so the function is undefined there. It is excluded. So our number line shows included points at 2 and 2 and an excluded point at 0. Step 3. Test a value in each of the 4 intervals. First interval, x less than 2. Let's test 3. We get a negative result. Second interval, x between 2 and 0. Let's test 1. We get a positive result. Third interval, x between 0 and 2. Let's test 1. We get a negative result. Fourth interval, x greater than 2. Let's test 3. We get a positive result. Our original inequality asked when the function was greater than or equal to 0. So we're looking for the positive results. The intervals that are positive are between 2 and 0, and from 2 to infinity. Putting it together, our solution is x is greater than or equal to 2 and less than 0, or x is greater than or equal to 2. Notice the parenthesis at 0 because it's undefined, and brackets at 2 and 2 because the function is 0 there. Let's summarize the key ideas and create a helpful table to review what we've learned. We've covered 4 main features of rational functions and their effect on the graph. First, a 0 in the numerator. Provided it's not canceled out, this creates an x-intercept. The graph crosses the x-axis at this point. Second, a 0 in the denominator that is not a common factor. This creates a vertical asymptote, a line that the graph approaches but never touches. Third, a common factor in both the numerator and the denominator. This results in a hole in the graph, a single missing point. Fourth, when solving inequalities, both zeros of the numerator and denominator act as boundary points on the number line, dividing it into intervals that we must test. In this video, you learned how to find the real zeros of a rational function and use them to solve rational inequalities. These skills are essential for understanding the behavior of more complex functions in precalculus. Finding zeros tells us where the function crosses the x-axis. Asymptotes tell us where it's undefined, and together, they form the critical points we need to analyze inequalities. Keep practicing these steps, and you'll become an expert in no time. Thank you for watching.